DOE CSGF Fellow Clay Sanders in the field of Civil Engineering and Computational Mechanics at Duke University.
Hi, my name is Clay Sanders, and I'm in the Civil and Environmental Engineering Department at Duke University. And today I'll be talking about inverse problem-inspired approaches to structural design for dynamic response. Now, dynamic conditions are prevalent in nearly any engineered system. Automotive, aeronautical, robotic, or mechanical systems all face harmful vibration that can limit the longevity of structural components or threaten structural integrity itself. Computational optimization tools like topology optimization can be useful in the design process because they can determine the optimal shape of structures to have the desired dynamic behaviors, like minimize vibration at certain frequencies, or in more unique applications, wave focusing or wave attenuation properties. And with the advent of 3D printing or additive manufacturing technologies, the complex geometries that topology optimization tools produce can be fabricated with high precision. Though while topology optimization does have great potential in the design process for structures that undergo dynamic conditions, there are several mathematical and numerical challenges in existing approaches that have limited its utility. So one of the kind of major themes of the talk that I'll be giving today is how we can seek inspiration from a related class of problems, material parameter inversion problems, to seek how we can improve formulations for dynamic response design. So how is the structural design for dynamic response like ultrasound imaging? Though they might not seem directly related at the surface, they are actually formed as very similar problems. In ultrasound imaging, you'll have a set of vibration measurements, and ultimately you want to infer an unknown field of parameters, in this case the unknown material stiffness of a tissue region, by matching a computed response of your model to this set of vibration measurements. Now in design, we're doing a similar goal. We're trying to match the structure's computed response to a desired behavior by determining the optimal allocation of material within the domain. Both problems are posed as PDE-constrained optimization problems, where we try to minimize an objective that depends on the displacement evaluations. These displacements are governed by a set of PDEs that serve as constraints to the optimization problem. And we ultimately use large-scale gradient-based methods to solve these nonlinear optimization problems. We need to navigate through high-dimensional parameter spaces, as well as compute vibration behavior that is represented in large-dimensional state spaces. And finally, in steady state or frequency domain dynamics, we need to address or contend with the presence of resonance phenomena, or resonant conditions where vibration can become unbounded, which can pose significant challenges in gradient-based optimization methods, as I'll describe. So today I'm going to go over two strategies for improved topology optimization and for steady-state response that were inspired by approaches in inverse problems to deal with noisy data and resonance-based phenomena. The first is the modified error-in-constitutive-equations formulation for the design problem, and the second is an adaptive eigenspace basis strategy for design parameterization. Now, first, I'm going to do an overview of how these types of design problems for frequency domain response are constructed. Here we have our structural domain. There is a traction applied that depends on the frequency omega. And we're going to assume that the response of the body can also be described as harmonic. So we'll use the elastodynamic equations in the frequency domain to describe this behavior. Here we have our conservation of momentum equation, the negative divergence of the stresses, sigma, plus the mass inertial forces, gamma, minus applied body forces is equal to 0. We have boundary conditions on the Neumann and Dirichlet boundaries. And I'll highlight the two constitutive equations that appear in this model. The first is the constitutive equation relating the stresses to the constitutive tensor times the strains. And the second is the constitutive equation relating the mass inertial forces to the negative mass density rho times the frequency squared times the displacements, or essentially kind of mass times acceleration in the frequency domain. We will measure the response using an L2 norm of the displacements in a measured subdomain. Essentially, you can think of it as the squared amplitude of vibration that we try to minimize in a certain region of the domain. And we'll parameterize designs using a density-based formulation, where we have a design variable that varies between 0 and 1 everywhere to indicate either void or solid material. And we'll use kind of standard penalization models as well as filtering operations to encourage convergence to 0-1 designs, as well as to impose length scale characteristics and avoid mesh dependency in the solution field. Now, there are several challenges in dynamic design that I've alluded to. And the main one is the presence of resonances in frequency domain dynamics. I plotted the structural objective, the response objective, over frequency, and you can see at 2 frequencies here, there are what are known as resonances, where the excitation frequency coincides with the natural frequency of the system, causing an unbounded displacement response and then accordingly an unbounded evaluation of the objective. Now these singularities are kind of in between these singularities in the objective space. You can think that there will be local minima into which gradient-based methods can easily get trapped. And if you're designing for multiple frequencies, you're going to be kind of superimposing different harmonics on top of each other. So this will kind of create even more treacherous space to navigate while you're trying to minimize the objective. We also need to consider the static stability of the design. Without a constraint on the static displacements, we can get designs like this, where the cantilever beam becomes unconnected or disconnected from its supports. And even if we design for both static and dynamic designs, just by minimizing that L2 norm of the displacements, it's going to be a very difficult optimization problem to solve. And the designs we obtain tend to have poorly defined features with kind of extraneous floating regions. So the first strategy that I'm going to present is called the modified error-in-constitutive-equations strategy, the MECE strategy. And the main idea is this method is that we're going to introduce a model relaxation into the optimization problem. And we're going to also modify the objective function to include what are known as error-in-constitutive-equations functionals. So here we have a new optimization objective that we're going to minimize. It's the sum of our original structural objective D and 2 error-in-constitutive-equations functionals. Now these ECE functionals essentially quantify violation in the constitutive equations that govern the elastic behavior. So that the stress is equal to the constitutive tensor times the strain. And in the dynamic behavior, that the mass inertial forces equal to negative mass density times omega squared u. So essentially, our objective function now is the quantification of 2 types of model error, elastic and inertial error, with our original structural objective. We're going to relax the enforcement of the constitutive equations and the original PDE constraint, and instead minimize these ECE functionals to enforce the constitutive laws. We're going to weight this minimization of model error against the original structural objective using a scalar kappa. Now this strategy has several mathematical benefits that make it powerful in design for frequency domain dynamics. The optimality conditions of this problem yield well-posed coupled variational problems and representing fully coupled forward and adjoint problems. Now these problems are well posed even at what would normally be resonant conditions. So we can always obtain unique values for the displacements or the forward variable and the adjoint variable at any value of the design. The objective function can then be evaluated at any point in parameter space. So it's not going to exhibit those resonant singularities that were causing trouble earlier. Ultimately, the objective will appear more convex in expanded regions of the parameter space. As you can see in these objective plots here, the original least squares has multiple regions where there are local minima, whereas the MECE objective appears more bowl-like and will be an objective that's more amenable to minimization. The challenges that we encounter are kind of the selection of the kappa parameter that will ultimately kind of govern the amount of model error that's tolerated, as well as that we need to solve a 2n by 2n linear system to solve these coupled system of equations. That's going to be the kind of the primary computational bottleneck in this problem. But we can revisit a multi-vibration isolation problem. This is that design I showed earlier. This is the design we obtained with MECE. Evaluating the objective over frequency, we can see that the MECE design attains strict minimizers of its vibration behavior at the two target frequencies. And we can actually visualize this behavior to see that the MECE design is able to have kind of minimized vibration in the target subdomain while experiencing unique vibration behavior elsewhere. With the help of some undergrad students, we actually did some 3D printing tests of this type of technology. Here we designed a bar that was undergoing axial base excitation. And at the right end of the bar, we wanted to see how a minimized vibration behavior. This is because we wanted to visualize the behaviors. We constrained a void at the end of this bar. We can see the vibration behavior of this structure. The in-plane vibration enables near zero vibration at the kind of perimeter of this void. And in an experimental setup, we wanted the void to contain sand so we could visualize the vibration. We designed this structure to have minimized vibration at a frequency of 3000 hertz. So you can see at this lower frequency, there's a lot of vibration in the optimized structure, while the control doesn't have much vibration. However, closer to the target frequency, where the control was predicted to actually have a resonance, you see much lower levels of vibration in the optimized bar. Now, the second method that I'm going to present today in the remaining minutes is a technique to reduce the design dimension in topology optimization problems. And here we're going to seek inspiration from a recently developed method for parameter inversion problems called the adaptive eigenspace inversion method. And the main idea in this strategy is to represent your parameter field through a sum of few and adaptively constructed eigenfunctions of a particular elliptic operator that you define over your same design domain. In this strategy, the density field is represented as a linear combination of adaptively constructed eigenfunctions. So our design variable is only going to be the coefficients in this expansion rather than the element-wise densities we would normally solve for. And this will represent both a significant reduction in the number of design variables you're searching for, as well as this restriction to a finite basis will impose length scale regularization that will avoid the need for the filtering operations that you would normally need to do throughout the optimization process for a normal topology optimization problem. So I'm going to show a quick example of how these adapted eigenfunctions are constructed. You'll start out with an eigenbasis that represents kind of a series of sinusoids. However, through a multi-stage optimization process, you'll obtain a solution using one basis and then construct a new basis using your current solution. As you go through multiple adaptations, the basis functions become essentially conform to your current solution and are able to represent piecewise constant fields in very low dimension, as the high index eigenfunctions represent very particular regions where the solution is going to vary. So this will represent a very efficient basis to represent a solution to a topology optimization problem. So here's just a quick example of using adaptive basis adaptation to reduce design dimensionality. Here's a design for a cantilever beam undergoing just a static force. And we'll use multiple optimization passes. And you can see here that the number of eigenfunctions in each pass is going to decrease. By the end, we solve our design with only 91 design variables, achieving a similar structural objective response and in far fewer iterations than the original conventional density method. Finally, we can solve an MECE optimization problem using this type of design basis. So we'll have our original optimization objective and add a regularization term that we use in these types of AEB problems. Here's the evolution of the design. You can see as it initially there's kind of a sinusoidal behavior to the structure density field. But as it goes through, you ultimately converge to a well-formed black and white solution that maintains the multi-frequency vibration behavior that we wanted to design for. So in conclusion, I've presented two new techniques for construction of topology optimization problems for dynamic response. The MECE strategy enables convergence to superior solutions through a model relaxation and objective convexification. The AEB method significantly reduces the design dimension by using an eigenfunction expansion representation of the design and imposes implicit regularization on the design field. Combined, these methods offer potential for efficient and robust dynamic frequency response design. Before I leave, I want to make a few acknowledgements. I first want to thank the generous support of the DOE CSGF program over the past 4 years and the wonderful help from the Krell staff. I'd like to thank my advisor, Wilkins Aquino at Duke, collaborators on this work, Tim Walsh from Sandia, Mark Bonet from ENSTA Paris Tech, and Julian Norato from University of Connecticut. And finally, some undergraduate students who helped me, Lourdes Reyes and Iris Chang. I would also like to thank my practicum advisors at Sandia, Jeremy Templeton and Reese Jones. And then finally, Chris Sponberg, who provided the optimization algorithm that was used to produce some of these results. Here's some key references, and happy to answer any questions.